Hello, welcome to CSC 351 Introduction to Data Science. Today's topic is about neural networks, and in particular feed-forward neural networks. So as many of you may be aware of, in today's big data science problems, the most popular classifiers that we are using for prediction tasks are from the class of neural networks. In this video, I'll try to give you another perspective of neural networks and basically show that neural networks are nothing but some sort of matrix transformation and applying some nonlinear function on the output of the neural networks, and then how we can train a neural network based on what we discussed earlier, gradient descent algorithm. And then at the end, I will show you one example, an implementation of a feed-forward neural network for a toy example in Python using TensorFlow, and then we see the results. So let's again look at the classification problem. Classification problem using neural network is similar to the way we define the classification problem, with a very minor difference. In here also we have a input vector or a feature vector. However, on contrary to previous definition that we map an input feature vector to a scalar, in here the input feature vector is mapped to an output vector. So therefore the input is a vector of dimension p, where p is the number of features, and then we apply a function, and this function will map this one to another vector which is called y, and then this is the this arrow at the top shows this is a vector. So this vector, however, has a particular structure, and this vector is a unit vector. We previously defined what is a unit vector. A unit vector is a vector that all of elements of that vector are 0 except 1. So unit vector. So y is basically the general form of y is somehow 0, 0, and somewhere there's a 1, and then 0, 0. All the other elements are 0. Note that this is not a general standard format for an output of a neural network. Sometimes we use only one node, one binary node, but in order to be compatible with the today's scientific library for training neural network, we use this convention, which is now used for all famous neural network libraries like TensorFlow or others. So this is a unit vector. So this is also called, this model, when you have an output which can take a limited number of labels, like y1, y2, y3, and yk. These are the number of labels. Therefore, we can present this one as for each sample as a unit vector. So basically, if you have k label, then we create a vector with dimension of k, and then for each input feature we have a label. We just only set that element of corresponding to that label to 1 and all others 0. Let's say for an input vector of 30, sample 30, the output is 4, label 4, and we have 6 labels. Therefore, this vector has a dimension of 6, so 1, 2, 3, 4, 5, 6. The fourth element is only 1. So 1, 2, 3, 4. This element is 1. All others are 0. This is how we form this, what is called one-hot encoding. So for now, the classification is we have an input vector or a feature vector, and this is mapped to an output vector, but this output vector is a unique vector, which means that only one element is non-zero, and then that element is 1. So then the goal is, if you have this pair of input and outputs for n samples, then we wanted to find a function such that we can estimate for new input vector, feature vector through label. So then we wanted to find appropriate function. So this is a general tacit classification. But neural networks, they use only matrix transformation and also a deterministic nonlinear function for this task. So they are basically, the entire process in neural network is some matrix multiplication and also some element-wise applying some nonlinear function on the output of this transformation. Then you can estimate the function using these operations. Why neural networks are so popular these days? Because as I said, we are dealing with big data, and this when it comes to big data, computation and speed play an important role. And then today's GPUs and CPUs are optimized to do the matrix operation, like matrix multiplication, and also we can take advantage of the distributed computing. Therefore, we can solve problems of having around like 10 million or 100 million parameters and train the model and obtain these the parameters. So let's see how we can, how using matrix transformation and applying nonlinear function, we can estimate function f, and this is in context of a neural network. So note that many other notes, lectures, they start looking at neural network as something that mimicking a neuron in our body, and then how the story started. But in here, I would rather take another angle to look at this problem, namely based on only matrix operations. There are rich contexts on the history of neural network, when it started, how it evolved and proceeded to the date, and what is the connection between our neuron and the neural networks, and how they are mimicking them, and what is the differences. But in here, I opted this approach because when it comes to implementation and understanding the software, we only deal with some matrix operations. So we need to know how these matrix operations are working together in order to build a neural network. So the first process in neural network is transforming the input feature to another vector, another representation, using a matrix transformation. So when we talk about linear algebra, we talk about if you multiply a vector by a matrix, basically you do some sort of transformation to that vector. Either you rotate that vector, or compress it, or stretch it. So the first step in a neural network is taking the input, and here we denote the input as a vector of dimension p. That means we have p input features. You can imagine if you have an image, the like 10 by 10 pixel, then you have a vector of 100 pixels. Then this vector is an input to the neural network. Then we apply a matrix transformation by multiplying from left to this feature vector, this matrix, which is, we call it W, an acronym for a weight matrix. And then there's some notations because I wanted to keep the generality, and also if you want to extend it for more complicated models. So in here, W's, so we have a subscript which shows the number of row and columns. Number of columns are equal to the number of features, and number of rows equal to the number of the transform space. So usually what we do, we get a huge feature vector. Let's say the feature vector is of dimension, let's say P is of dimension of 10,000. Then by having this matrix multiplication, we wanted to map this vector to M1, which is 100. So basically we transform, we project a feature vector to another dimension or another feature space or another representation or another encoding of this vector. So in today's neural network, in particular when the so-called attention-based models are so popular, this is called encoding part of neural network. When you get a raw feature vector or raw measurements from an observation, and then using a matrix multiplication, you map this feature vector to a new dimension, which is called encoding. Basically, we encode the feature space of dimension P by M. It is usually P is greater than M1, but in some other contexts, we may also map it to a higher dimension. So it's not a must. But usually we decrease the dimension to have a more compact form. Examples, if you have an image of no dimension of 1,000,000 pixels, you wanted to encode it to a vector whose dimension is thousands, right? You wanted to keep important information. Or in sounds, if you're applying a Fourier transform of dimension 512, you may map it to a smaller dimension of 64. So that's the first step in neural network. We get an input feature, we multiply it by a weight matrix, and this weight matrix will encode to a new feature vector. We call it S in here. Note that the superscript in here I use for W and S denote the first step of neural network. So we can imagine if this is X, this is the input, it goes to the first transformation by W1, and then we'll give it the output, we call it S1. Why we call it this superscript? Because this process, there might be a change of transformation, because after this I may have another stage of W2, I may have W3. It depends on how many layers I'm gonna to use, okay? So in fact, if you have lots of layers, this problem now become the so-called deep learning model, when you are projecting the data to different encoding in order to let with number of parameters that try to memorize the patterns and do the prediction for you. But for now, assume that we only have one layer. In this layer, the first layer is usually called hidden layer. So in neural networks, we have input layer, we have hidden layers, when we have the output layer. We have one input layer, we might have more than one hidden layers, and we have only one output layer. So in here, we consider one input layer, one hidden layer, and one output layer. So for now, we are in the first step when encoding the input feature vector to another vector whose dimension is M1. And then as the superscript shows that we are in the first step. So in a more compact form and a matrix representation. The vector x is transformed to vector s1, and then we have also using the transformation of matrix w1. So dimension wise, this is p by 1, this is m1 by p, and this one is m1 by p. Have this. So this is the first step. So this is a linear transformation, but as I mentioned, the neural networks are a cascade of linear transformations as well as nonlinear transformation. So after we compute this encoding and we have the vector S1, then we apply a nonlinear function to each element of the S, and this nonlinear function is called an activation function. It is called an activation function. So there are a number of reasons why we are using this nonlinear function or activation function. The activation function is basically taking from our neuron. So basically in our neuron we have some stimuli that input to the neuron, and then neuron, if you get to a threshold, a neuron fires, and then this basically based on some input stimuli, the output will be activated. So this activation function is a nonlinear function. That's one reason. The another reason is if you don't apply any nonlinearity into the neural networks, then we have only a cascade of matrix transformation. We can basically put them all together as a simple linear matrix transformation. And then this linear matrix transformation is not that much powerful to model non-linear classification problem. So we know that many classification problems are non-linear, so therefore only matrix transformation is linear. So that doesn't add that much if you had more than one layer of a neural network. Another reason is when you are doing a linear transformation, the output might be unlimited, unbounded, and then that's not good. So the problem may be get really unstable. So by applying a nonlinear function, we can bound the output of a one layer neural network. So if the input is from infinity, minus infinity to plus infinity, the output is always from -1 to 1 or some other limits. So as you see in here, we get the S1 from the first transformation. We apply this function element-wise to each element of this vector, and then we get the output of the hidden layer. So note that when we are talking about the output of a layer of neural networks, there an output before applying the activation and an output after applying the activation function. When we talk about the output is after applying the activation function or nonlinear function. If I wanted to show it in the matrix form, so basically you have a vector, you apply a nonlinear function, or we call it from now on the activation function, and then we get the vector h. So this is an output of the first layer of neural network. So this is what we have done so far. So we have an input layer. Basically each node in here shows one input feature or input variable. In here the number of units in each layer is p, and then number of layers in here 2. The first layer is an input layer, the second layer is hidden layer. So for this example, we have one input layer, one hidden layer, and one output layer. This can be easily extended to multiple hidden layers. So the output of this hidden layer basically is h11, and then h21, and then h31, and then the last one hm11. right? So these are the output of this hidden layer. Each node represents one variable. So when we talk about the layers, that means how many hidden layers we have. When we talk about the unit, we wanted to know how many units we are using per each hidden layer. So in here, number of units for this hidden layer is M1. Okay, and as you see that most of the books and texts, they use these graphical representation of neural networks, where you have each node represent one variable, and then each node is basically connected to all other hidden units, and that basically what we do is a matrix multiplication. This is the process of encoding the input feature vector to HN. So far this is the first step in a neural network, in particular the feed-forward neural networks. So then the question in here, what is the activation function? So activation function, there are a number of different activation functions that have been proposed since 1983, and then these activation functions there are some nonlinear activation functions. So the first one is basically identity, which we never use, but in order to at least be completed. Then we have a binary step, we have logistic, we have tangent, arctangent, rectify, linear, unit, and we have the other types of activation function. But the two most important activation functions that in today's state-of-the-art model are used is these rectify linear unit, or we also call these logistic or soft step, or sometimes we call it also sigmoid activation function. These two are the most important activation functions we are using. When you're implementing a neural network, the software allows you to choose the type of activation, and then you can, usually the norm is you use a sigmoid, or you can use also a rectify linear unit activation function. So it's only a nonlinear function which apply to the output of the matrix transformation. I told you why we are using the activation function. Now we can do this process for multiple steps. After this, again, we can have another matrix multiplication. We can apply another activation function. We can do this process multiple times. Depends on number of the hidden layers we have. If we have 10 hidden layers, we need to apply this process 10 times. And also we note that the number of hidden units in each hidden layer might be different. So sometimes we start a process from, let's say if P is 10,000, the first step H1 is then 5,000, and then hidden layer 2 decreases to 200, and then third hidden layer to 64, and then we have the output. So how we choose the number of hidden layers and how we choose the number of hidden units per hidden layer, it's a matter of practice, and how if we get a skill and mastery and experience in neural network, you probably come up with an idea how many hidden layers and hidden unit I should use. So some people think if we increase the number of hidden layers and units, basically we have more parameters, and then that increases the capacity as a neural network to memorize more patterns. But it's not in general true. Based on many research papers and publications, they show that increasing the number of hidden layers doesn't necessarily increase the prediction performance, and also that will add more computation, which is sometimes is really cumbersome and not practical to increase the number of hidden layers. So Um, then after this first transformation, now we wanted to compute the output. Computing the output of neural network, knowing that the outputs are some sort of unit vectors, that because you use one-hot encoding, is a slightly different from hidden layers. So let's say so far we computed the output of the first hidden unit. So this one shows the first hidden unit, and H denotes the output of the first hidden unit. So basically we have the input feature vector, we have the first hidden unit, and the output of this unit is the vector 1. Now we wanted to apply it to another transformation or another layer. This is output layer, and then we're going to get our output vector for one particular sample. Okay. So in here I use the superscript W2 to show that this is another matrix transformation in order to distinguish that one from the first step. So then we basically map the first step is use a linear matrix transformation to transform the output of the last hidden unit to the what is called, in here I use the S vector. So note that the dimension of the output layer is k. That means I have k nodes or k variables or k label at the output of neural network, and for each sample one of these units, it just becomes 1. All others are 0. So that shows that this input vector correspond to that output label. Okay, so but I haven't done yet in here because we only apply the linear transformation. Have in mind, when it comes to neural networks, you have one linear matrix transformation followed by a nonlinear transformation. And here also we need to have a nonlinear transformation. But for now, there is a linear matrix transformation. The output of the last hidden unit here is 1 because we have only one hidden unit, is multiplied by the matrix W2, and then we get S2. So then how to apply the nonlinear function to the last layer to get the output? In here, instead of using the normal activation function, we use what the so-called called the soft mask. Soft mask is also another nonlinear function, which is basically gives us a probability for each output unit of the last layer. So it's important to note in here what we get for the output of each unit. So we have different unit or variable. So we call some from 1 to k, and we know that only one of these variable or unit or label should be 1. All others should be 0. Right? But what we wanted to compute in here, probability that each of these nodes is 1, probability of each of these. Ideally, let's say if this node is 1 and all other nodes are 0, in practice for actual label, this is basically y. But what we compute is probability that this node, the y1, equal to 1. Probability that the y2 equal to 1, probability that y3 equals to 1, and probability that yk equal to 1. So what you wanted to get is probability should be 1 and all others 0. Right? This is an ideal case. But in practice, what we get a high likely probability for this node, and all other nodes are small probability. Let's say in practice what we get in here is like I get 0.1, 0, 1, 0.1, 0, 0, 5, 0.1, 0, 0.05, and then this one is 0.98. Okay, that's because this node has the that's a highest likelihood among all these nodes, and then we know that the sum of these should be add up to 1. So we were looking for a function that first has a property of a probability when the sum of these all the units, the probability add up to 1. So the most common function we use is called softmax. A softmax is divide after you did the last linear transformation for output, you applied this exponential function. So for the kth unit, we get the exponential of sk for the second layer divided by sum of the exponential of the all units. Note that this thing here, this 2 doesn't mean square. Does not mean square. Okay, that's the label of this is labeled the second state label. So therefore the output of the neural network in here is the probability that that unit is on or off. So because we convert the labels to hot one encoding, and now we compute for each label which one is 1 and 0. This is very important because usually this is a little bit ambiguous and not very well explained about the output. Some textbooks, they use only one variable, but when you wanted to implement, you see something like a one hot encoding, convert the output vectors to one hot encoder labels. Then you should know that mathematically what we are doing. We basically, instead of finding the actual label, which is a unit vector, we find the probability vector, which shows the probability each unit is 1 or 0. So that's basically we are done. We are done with the neural network, and this is for feed-forward neural network. But this practice of linear matrix transformation plus applying a nonlinear function, either activation or softmax, is repeated for all sort of neural network. If you're using the convolutional neural network, if you're using the recurrent neural network, they all use the same concept with a little bit of tweak and change in the architecture of neural networks, but the basics are the same. So I can say in today's the 3 most popular neural networks are feed-forward neural networks, convolutional neural networks, and recurrent neural networks, and their extension like LSTM or GRU, which are part of the or bidirectional recurrent neural networks. They're all using the same concept. You have a softmax, you have an activation, and you have a linear transformation with a little change in the architecture of neural network. So we have 3 steps. The first step is to map the input vector, encode the input vector to another vector, and we're encoding favorably to lower dimension, and then we repeat that step a couple of times, depends on number of hidden layers, and then at the end we have the output layer, in which instead of using an activation function, we use a softmax function, which gives us the probability that one unit of this vector is 1, and then we basically choose the one which has the maximum probability and set it to 1. For instance, for this example, this one is chosen, this label chosen as the correct label for this function. So far we just discussed the neural network in a way that the weight matrix or these linear transformation matrix elements are known. So in fact, if these elements are known, then the entire process of neural network is doing 3-4 matrix multiplication, apply nonlinear function, and then find the label. But the problem is we basically set we don't have these weights, we don't have the parameters. We need to find the parameters based on the label data we have. So we have a pair of data x and y for n samples. Then we wanted to see how we can find these matrices. So this matrix is not known, and also this matrix is not known. So these are parameters. These are unknown parameters we need to compute, unknown parameters. So if you have, let's say we have a neural network with two hidden layers. So we have the first hidden layer in here, and then we have second hidden layer in here, and then we have third, this is the output. So here is x, this is h1, this is h2, and then in here we have y. So we have a matrix in here, we have a matrix in here, we have a matrix in here. Okay, so all these parameters are unknown. We need to find these parameters, and how to do it the way I showed you in previous example. Using optimization, we define a loss function or objective function, or also known as a cost function, and then we try to minimize this cost function in terms of these parameters or weights when we obtain the weights. Perhaps the most difficult task and also most time-consuming task in neural network is training a neural network, in particular for very heavily task. For instance, for a speech recognition that you're using in Google, they have 2,000 hours of speech in order to train the model, and usually the training takes around like 3-4 weeks to be completed. So therefore, we wanted to show you how we found the how we can find the parameters. And parameters are the weights of these linear matrix transformations. Okay, so the loss function we are using in here, because the output of neural network is a probability, the output of this neural network is a probability, then what we are trying to optimize is, instead of using the mean square error cost function, which basically try to minimize the actual label with the predicted label, we now have a probability. So what we use in here is called the cross entropy. Cross entropy basically is a probabilistic distance measure, which shows that how two probability are close to each other. So one probability is the probability of actual data, then that gives us one unit variable is 1, all others are 0. The probability are all other nodes are 0, 1 is 1, and then we have a probability that obtained from this function, which consists of some matrix multiplication and nonlinear function. So in order to minimize the difference between actual probability and estimated probability, we use the cross entropy. Entropy and cross entropy are very vast and deep field of research and study in communication and also computer science. They have been proposed about 70 years ago by Shannon, and then there rich literature in particular in communication theory, and they have been used 40 years ago for coding and mobile computing. But in here, just know that cross entropy is a probabilistic measurement to show how two probabilities are equal. And this cost function in here now is basically a multiplication with the actual label and the log of the probability that we obtain from the neural network. So what is this? In here, K is the kth unit. I is the I sample. How many samples do you have? Let's say we have 1 million training samples. This is the ith one. And in here, this is a probability of this unit and sample, that the probability this is equal to 1. This is 2, 1. And this multiplication, we know that for all other units, this is equal to 0 because this sample is only for one unit is 1. And then basically for one sample, we only compute 1 log probability. And then this is the cost function. And in here, what are the parameters? This is very important. We have W, but we don't see any W in here, but we know that in order to compute this probability, we multiply the input feature vector by this linear matrix transformation and applying the nonlinear functions. Nonlinear functions are already known. The only thing we need to unknown is the W or weights or parameters of neural networks, which are the elements of hidden unit matrices or input and output matrices. Therefore, the cost function, the loss function, is a function of W. Now we have a loss function and we wanted to optimize this. We already talked how to optimize a function. The technique we are using in here is gradient descent algorithms, in which we basically need to compute the gradient of the loss function and then update the weights based on this gradient. If this gradient is positive, we are taking a step opposite of that gradient, and then we use a learning rate, and then learning rate basically adjusts the steps we need to take. This is also very sensitive parameters in order to converge quickly. So this is the basically gradient descent algorithm. Mostly in today implementation, we use a stochastic gradient descent algorithm in which the cost function is only computed for one sample. Gradient descent algorithm might be takes more steps, but because computationally is less expensive than the gradient descent algorithm. And the other advantage is we can do parallel processing, which extremely speed up the training phase. So the next question in here is, okay, so I use the gradient descent algorithm. How do I compute the partial derivative of a cost function with respect to weights elements, or elements of the linear transformation matrices? In fact, this is a fundamental question in neural network, and a breakthrough in how to compute this gradient lets that we can now use this gradient neural networks very efficiently. So there was a technique proposed by 3 scientists, and this technique called backpropagation. And backpropagation basically is a technique that will allow you to compute the partial derivative of loss function with respect to weights of neural networks or parameters of neural networks. So this is very important to know, because we sometimes get lost. We confuse backpropagation with the gradient descent algorithm. So if you take this step, then you never confuse them. So we have some linear transformation. We need to find the loss function, and then we need to do the optimization. Which optimization technique we are using? We use gradient descent algorithm or their extension. When we wanted to solve the in this optimization using gradient descent algorithm, we need to take a derivative of the cost function or loss function. How to compute this derivative is using backpropagation. So I will not talk in here in this video about the backpropagation, but I will give some external references. In particular, one very nice animation that will show you how the backpropagation works. So you probably never implement the backpropagation techniques. They're all implemented in the software, but you should know intuitively backpropagation technique is basically is a model that lets you to compute the gradient of the loss function. How? By using the change rule in the gradient partial derivative. So it will split the derivative of the loss function using the chain rule, and then make it simpler, and then it will basically back propagate to weights of the initial weights and let you to take the derivative with respect to all weights in different layers. So I will upload some external reading material for back propagation, but all you need to know the steps of we take in order to build a neural network, and the steps to train a neural network. And when you are using the software, you should know what are these concepts and what you are doing. So, and also we talk about the importance of the learning rate, and in today's mostly we use the stochastic gradient descent or Adam algorithm in order to do this as an optimizer to find the weights of the neural network. So put all this together for our simple example. When we have one hidden layer, this looks now this process of a graphical representation of our neural network, and also the matrix transformation process along this way. So basically we have an input feature vector whose dimension is p. In here, this could be any feature vector. It could be some measurements on patients. It could be an image. It could be voice. It could be some financial data. It could be any other measurements from weather or some other natural phenomena. And then the output is some labels. And then for each input feature vector, we have one output, and this output is a one hot encoded output, meaning that all elements are 0 except one element. If you are still not sure about one hot encoding, please refer to an external another slides I uploaded on Blackboard on one hot encoding. And then we do the first round of transformation using W1. It's simply a matrix transformation. Then we apply in here the nonlinear functions, and then we get H1, and then we apply another, we multiply by another matrix, which is W2, and then in here we apply the soft mask to each unit of output layer to get the output. So the entire neural network consists of some linear matrix transformation, some applying known activation functions, and then for output layer we use soft mask function. So if you have more than 2 hidden layers, then you can do the same process. So here it's a neural network with one input layer, and then we have H1, H2, H3. This is 3 hidden layers. 3 hidden layers. How many units per hidden layer? Then you need to count this. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 units per hidden layer, and these numbers could be different for different layers. So when the number of hidden layer increases, we call this one deep learning. So deep learning is nothing but a dense and multiple layer of the neural network is called deep learning model, because we have a deep representation or deep encoding of a vector, and these in here we have different linear transformation. We have W1, W2, W3, W4, and we have a nonlinear transformations, and then we have the output. As the number of hidden layers increases, the number of also neural network parameters increases. That means more training done, more data. It's important to know that the balance between these two. If you have a huge neural network, you also need more data to train this one well. Another way of looking at neural networks is some sort of the neural networks are machines that memorize patterns. So by having these parameters are tuned somehow like a memory to memorize different patterns, and we would like this neural network to generalize for unseen patterns, which in practice it has been shown if you have good enough data, neural networks can unbeatable, and they give you the best performance. Having said that, neural networks are not appropriate for all applications. There are some applications in which we don't have enough data, and then you should go and look for other type of classifiers. You should use a decision tree, for instance, random forest. They are much better than neural networks. But the take-home message is, if you have big data, I think the way to go is using neural networks. And then what kind of neural networks you should use, feed-forward neural network or recurrent neural network or convolutional neural networks, it also depends on application. A very brief discussion about the type of neural networks we need to use. If you have a classification problem which doesn't deal with the, is not dynamic, is not a time series data, then you can use feed-forward neural network. For image applications, it has been shown that convolutional neural network, which are very slightly different from feed-forward neural network, perform well, because they do one more encoding and filtering inside that also you have more and better representation, hidden representation features. But when it comes to some time series data prediction, like speech signals, like some other like language models and stock market prediction, then when you have dynamic, when the data depends on previous time step, then you should use the recurrent neural network. I will have another video on recurrent neural network and how they work, but all of them works based on linear matrix transformation, as well as applying a nonlinear function, and then the optimization, softmax, loss function, and then using the gradient descent algorithm and backpropagation. This is common within all neural networks. So here is a summary of the steps. So there are usually 6-7 steps when you're training a neural network. So because we don't have the weights means the W's, we usually set up the W's to some random values. These random values usually are taken from a universe distribution from 0 to 1. So all the weights of all matrices, they set to a random. So then we do the feed forward. Using it, having this random, we compute the error, and then we have the loss function. This is the jth we describe in here, jw. And then we have the desirable output. These are the v vectors for I equal 1 to n. And then we calculate the derivative. So this is basically what you do, the gradient descent algorithm. Gradient descent algorithm. And then how to compute the derivative using backpropagation, and then update the weights. We here update the weights. So basically weights for step t plus 1 equal to weights from step t minus learning rate, partial derivative of the cost function with respect to that weight. So let's say this is weight I and j, and then j, partial derivative of weight I and j. So then we repeat this process for a number of epochs until the method converges. So how to convert, I told you, we can set the maximum number of iterations reached, or we don't see any improvement in weights, or another criteria is when you get a good performance. So this is more common because we don't, mathematically we wanted to find the local minimum and all, we're going to find that weight doesn't change, but we wanted to stop somewhere the results are promising. When let's say if you do an image classification and if you get a performance of a 99.9%, then you can stop the training phase and you're done. So it also depends on the output, what is the performance, rather than checking the gradient descent algorithm converges or not. There are actually the other techniques. The techniques we're using is we use some validations and then we compute the error and then we do what is called a early stopping in order to stop the training neural networks. There are a number of other ways to how to train neural networks, but for here we just need to know the steps we need to take in order to train a neural network. So the early stopping, which is a very here we have error, so if this one shows error, and we first do training on some training samples. So these are a number of iterations in here. Iterations. So this is for red shows the train, and then we use some validation data. So for validation data, usually the model starts with higher error because these data are not seen by classifier, and then you also check it on validation, and then you see the results are going good. And then at some point, as we do more iteration, the error becomes more severe for validation. So blue is like validation data, train data, validation data. So we stop at this point, and then we stop the training neural network. This is called early stopping for neural network. So the reason is, if you keep continuing the iteration, we are doing overfitting. That means the model is giving very good performance on training data, but is not good for the validation data. So from this point onward, what you do is you're doing overfitting. So you should stop. This is called early stopping criteria in order to stop a neural network from training by checking the test and validation. You split the data to train and test, and or validation, and then you train on a trained model, but after each epoch you test it on the validation. So you stop where you get better performance where test, but the results doesn't improve for validation. This is called early stopping. So these are the 7 steps we usually take in order to train a neural network. Test phase is extremely simple. Basically, this is a pass of matrix multiplication applying nonlinear function, then we are done. So here I have an example. This example is, I forgot to put the link in here from the GitHub. If you refer to the Jupyter notebook file uploaded with this video on Blackboard, there is a link to this GitHub from one of the students. So this is basically a model in which we wanted to train a neural network on iris data. As I said, iris data are data that we have some feature vector. I think we have around 400 samples, if I'm not mistaken, and then features vector is p is a dimension of 4 or 5, and then the output k is 3. We have 3 classes. We wanted to train a neural network, a feed-forward neural network, to do the classification. So, as I said, we use a TensorFlow. You need to use the TensorFlow. We import the TensorFlow as TF. We also need to have other libraries. Then we first define some auxiliary function, this initial weights, because we need to set up the W's, right? W, in here we use a neural network which has one hidden layer, only one hidden layer. So we have one input. So let me put it, we use neural networks with one hidden layer. This is one hidden layer, this is X, and this is Y. Therefore we have one W1, one W2, and you have the input vector, input vector. Okay, and you have output, which is one hot encoding vector of dimension 3 for this case, if we have 3 classes. So first we need to do the initial randomization. That was a step 0 from the previous slide, step 0. We also, so that one basically create a weight matrix. This is what we do basically, the forward propagation by which we do the matrix multiplication. So for this one, we basically multiply the, if you go to lecture, we multiply W1 by X vector in here, and then we apply a nonlinear function, which is a sigmoid, and then this is the output H. And that one, after we have H, we multiply H by another matrix W2, and then we get output. This is output, not applied soft mask. We still need to apply the soft mask in here. Then we also have another auxiliary function to prepare the data. So we get the iris data, we load them, we get the label. This is basically X, this is Y, the target. And then here we get the dimension, number of samples, number of features. And then in here we wanted to create a one hot encoding. So this one is how we, so if we have, let's say, if we have 3 classes, let's say we have three classes, and then we have the, for sample 1 the class is 1, for sample 2 class is 3, for sample 3 class is 1, and then so on and so forth. We wanted to convert this one to one hot encoder. For each sample we create a vector, and then for this one this is 1 0 0. For this one the one hot encoder is 0 0 1. The third one, for this one the one hot encoder is 0 0 0. So this part basically create this one for you. So this is the data preparations, and then now we are ready to train the model. So you can practice on this example and then change the parameters, use it for different data sets, and then see how we can work through. So first we apply the get iris data to get the training data, input feature and training labels, and then we split data to test and train. We don't use any cross-validation in here. Then we get the number of input nodes. So this is, sorry, we have 4 features in here. P in here is 4, I made a mistake. P in here, yeah, P is 4 in here, I was right. And then number of hidden units for the hidden layer is 256, this number. So basically if you have a neural network, we have 1 2 3 4, and hidden layer we have 1 2 3, go all the way to 256. This is 4, and then output is 3. So then in here we initialize the weight. So for those of you who are not familiar with TensorFlow, in TensorFlow when you're creating a variable, you need to put in a placeholder. And so in here we create a placeholder for the weights, and then we create them, and then we compute the output y hat, and then in here we use a soft mask, and then after we do have the prediction. So in TensorFlow we basically create all functions we need, and then we create a session, and then we run this session. So we first create the cost function. This is the J, this is basically JW. The method we are using is we are applying the softmask cross entropy to basically to Y, actual Y, and this is the label Y and Y predicted. Y predicted, so that should be Y and Y predicted. And then you are creating a session. This is a must in all when you're working in TensorFlow. We need to create a session and then run that session. You also initialize the global. This is a default piece of code you should do, and then you run it. So that these steps are used for any sort of running a tensor. And then here we do the epochs or number of iterations, and in here it's 100 is number of iterations for the gradient descent algorithm, and then we do it for each sample. So basically we use here a stochastic gradient descent for samples within the number of training set. This is n for each one. Update the weights, do the updates. So we create updates in here. The technique we are using for the optimization is gradient descent. We set the the threshold to 0.01, and then we try to minimize the cost function, the j theta. The cost function is jw, is noted in the slide. And then we compute the training and test accuracy, and in here we print out the results. So basically for each in each epoch we go through all samples. We do one run of all samples, and then we repeat this process 100 times, and then we compute the accuracy of tests and training. This is exactly the graph I showed you in previous slide, the graph for test and the graph for training, and then we stop there. So in here we print out the number of epochs and then the accuracy for tests and training data. So if you go through the Jupyter Notebook file, run this code, you will see the accuracy for both train and test data, and this accuracy is pretty high for this example. So this process will be exactly repeated for any other examples. You should identify your input feature vector, number of samples, how many hidden layers you wanted to use, what kind of optimization you wanted to use, and then how number of epochs, when do you stop the training. But you can basically exactly copy this piece of code and then apply. You can also use the other softwares like KRAS. This is another deep learning one, which is much simpler, but TensorFlow is better because if you want to do some development and you wanted to create your own neural network, is much better. So I will highly recommend you to also, with this slide, take a look at the Jupyter Notebook slides, which has some other complementary materials and explanation on gradient descent. And also I will upload more reading materials and also slide on one-hot encoding and also gradient descent algorithm. What's important to understand the neural network from a matrix transformation perspective along with nonlinear one, and how to adjust the parameters and what kind of optimization technique you are using, and how to stop training a neural network, what is the best way to adjust a learning rate in neural networks. And these are the details that when you're dealing with big data, because when you're setting your parameters, you probably need to wait to 1 week to get the results. And if you want to try another set of hyperparameters, then it will take more and more, but it all needs your practice. Each data is different from the others. Type of neural networks are also important, but as I said, we basically use feed-forward neural network, recurrent neural network, or convolutional neural networks. So I think that's a very brief introduction to neural network, but that will help you to understand how the neural networks work and how to implement an example and see the result. I wish you all a good day or night, and I will see you in next video.